Hi gang, and welcome. It's Dr.B, the Chemie, and today I've written a single unit material balance problem for practice, and you can try it out by yourself, or if you want, the other part of this video is going to walk you through my approach on how I would solve this problem. Now, the name of the problem is Extractive Distillation of IPA. Now, IPA stands for Isopropyl alcohol. And if you're curious, extractive distillation is an advanced method of distillation, which you may talk about in thermodynamics, separations, or process design. But regardless, at the end of the day, we've got a single unit material balance problem that we can work on. So let's get to it. Let's look at this problem. So we've got isopropyl alcohol that is often used as a cleaning agent in the electronic industry. A semiconductor company called Linte wants to reuse the isopropyl alcohol for multiple cleanings. However, they've run into an issue where their leftover stream consists of only 32 mol% IPA and the rest is water. In order to properly clean their substrates, Linte needs a final product stream with at least 98 mass% IPA and the remainder can be water. To perform the separation, a pure stream of ethylene glycol is fed at a rate of 921 kilograms per hour into a distillation column at a ratio of 1 kilogram ethylene glycol for every 4 kilograms of water entering the column. The IPA water leftover stream is also fed into the distillation column. Exiting out of the top is the desired IPA water stream, and separately a mixture of ethylene glycol and water exits out of the bottom. And we want to know the mass flow rate and composition of all streams. All right. Now, if you want to, if you got some ideas on how you may go about approaching this problem and solving it, feel free to pause the video here and get to it. Go work on it, and then when you get your solution, come on down and tune back in to my solution. But if you're just like, oh, so eager and anxious and excited to find out my way of solving this problem, then keep on tuning in and let's go through it. So looking at this problem statement, I noticed that there's a lot of words. And especially if these are like your first batch of single unit material balance problems, it may be daunting for you to just look at all of this text and immediately try and solve the problem. So normally what my approach is when I'm trying to solve these types of problems is I'm actually going to break it down line by line. And I'm going to try and pull out all the useful information that I think is in my problem statement. And so we're going to do that first. So let's take a look, and we're going to break this down piece by piece. So we've got isopropyl alcohol is often used as a cleaning agent in the electronic industry. Okay, that's good background information, but I don't think I have anything that's going to actually help me solve this problem and figure out some mass flow rates and mass compositions. All right, next line. A semiconductor company called Linte wants to reuse the isopropyl alcohol for multiple cleanings. However, they've run into an issue where their leftover stream consists of only 32 mol% IPA and the rest is water. Okay. I've got a little bit of information that I can use. So we know that there's a leftover stream that has 32 mol% IPA and the rest of it is water. Okay, so we're gonna just circle that, we're going to mark it up, and we're going to save that in our back pocket for later. Moving forward, in order to properly clean their substrates, Linte needs a final product stream with at least 98 mass% IPA, and the remainder can be water. Okay, so looking at that sentence, again, it seems like I have a value that's going to be useful for me. We've got the 98 mass% IPA. And they also identified that that's going to be a final product stream, which using the word product would suggest that that's going to be one of our exiting streams. All right, moving forward to our next sentence. To perform the separation, a pure stream of ethylene glycol is fed at a rate of 921 kilograms per hour into a distillation column at a ratio of 1 kilogram ethylene glycol for every 4 kilograms of water entering the column. All right, so again, if we're just looking for numbers, we immediately see that we've got ethylene glycol being fed in at a rate of 921 kilograms per hour. We also have a little bit more information about the stream. It doesn't do a whole bunch for us, but it's still good to know. We also know that that ethylene glycol is a pure stream. So there's nothing else coming in other than ethylene glycol. All right. And then the next piece of information we have is that we have ethylene glycol is being fed at a ratio of 1 kilogram ethylene glycol for every 4 kilograms of water. All right. Now, you may also notice that that language is a bit different from the other pieces of information we've gotten so far. All the other pieces of information have either been a mass or a mole percent or a flow rate. And now I have something a little bit different, and for us, that's something I want to identify and acknowledge that this is a process specification. And so we may have to do a little bit of additional work to convert that into a mathematical formula. But we don't need to worry about that right now. I just need to know we have that information. Now, as we go through, I also know we've got a lot of known pieces of information, but I also need a little help in terms of how I'm going to approach drawing my diagram. And so what I'm also now looking for is language to help me identify how I should be drawing my diagram, so I understand what this process truly looks like. And we see in this most recent sentence that we have ethylene glycol is fed. Okay, so ethylene glycol is being fed into my column, which means that I have an inlet stream of ethylene glycol. Great. All right, and I think we've extracted as much as we can from this sentence. So we're going to move on to that next sentence. We've got the IPA water leftover stream is also fed into the distillation column. Exiting out of the top is the desired IPA water stream, and separately a mixture of ethylene glycol and water exits out of the bottom. All right, so I'll identify, just like you, that there's no numbers here. So it doesn't seem like I have any additional known pieces of information or perhaps a process specification. But what I do get from these sentences is information in how I should be drawing my diagram, my process flow diagram. And so we can identify that we've got an IPA water leftover stream is also fed into the column. So we know that we have another inlet stream. We have exiting out of the top is the desired IPA water stream. So we got one of our exit streams. And we have, and separately, a mixture of ethylene glycol and water exits out of the bottom. So we have another stream coming out the bottom of this column. Great. And so looking at the final sentence we got, which is, what is the mass flow rate and composition of all streams? All right, great. So that's our full problem statement. And we've marked up a lot of this statement to help us out with solving the problem. And as we go into solving the problem, there's a few steps we want to follow. So the first thing that I always do when I'm trying to solve these types of problems is I'm going to draw a diagram. I want to know what the system looks like. I want to be able to get a sense of where everything is and what I'm really solving for. So we've got our distillation column here, and I'm just going to recount all the pieces of information we got from the last slide in our problem statement. And I'm looking for those items that I boxed in the thick blue in the blue squares or rectangles. I'm looking for those pieces of information because those were the ones that just gave me the information I need for how to draw my distillation column. So we've got ethylene glycol is fed at a rate of, and I don't need any numbers right now. I just need to know where are my streams, what's going in, what's coming out. So since I've got ethylene glycol coming in, we're going to draw an arrow going into my distillation column of ethylene glycol. The next thing we have is that the IPA water stream is also fed. And if you don't remember, it's the leftover IPA water stream that's going to be fed in. And that'll be important information when we start to identify and write in our notes. But for now, we've got an IPA water stream coming in. Great. We also know exiting out of the top is the desired IPA water stream. So again, we have another IPA water stream coming out of my column. And the last piece of information I had in terms of how to draw this diagram is that Separately, a mixture of ethylene glycol and water exits out of the bottom. And so we're going to draw an arrow that comes out of the column from the bottom. And so now I have a diagram. I know where all of my components are. I know which streams have what components. And that's really great because now the next piece of information is we're going to identify we're first going to number our streams. So we're going to number them. So we're going to start from the left. We're going to focus on the inlet stream. We got 1 for the IPA water stream coming in, 2 for the ethylene glycol stream coming in, 3 for the IPA water stream coming out, and 4 for the ethylene glycol water stream coming out. Now that I've identified all my components in all streams, I've labeled all my streams, the next thing we're going to do is we're going to identify my knowns and my process specifications. And we're going to convert this information into variables. So we've got first that the waste stream contains 32 mole percent IPA. And so remember, when we write a mole percent, we're going to write it with using the variable y. And we've got a subscript of 1 comma IPA. So the mole percent of IPA in stream 1 is 0.32. Or the mole fraction is 0.32. Next, we have that the final product stream has at least 98 mass percent IPA. And when you see language like that, it has at least this mass percent, most likely you're going to be working with that mass percent. So when I say at least 98 mass percent, it's 98 mass percent that's going to be exiting the column because that's the bare minimum I need. And since we know the composition for stream 3, we're going to write X3 comma IPA equals 0.98. Now remember that X is when we're using a mass percent or mass fraction. Okay, and notice again we've got a Y for mole percent and we've got an X for mass percent. So that may come back in a little bit and we may have to reconcile those differences. But for now, we just need to identify our nodes. Moving on, we know that ethylene glycol is fed at a rate of 921 kilograms per hour. All right, and so that's, since it's being fed in, that's stream 2. And so we know the mass flow rate of stream 2, it's 921 kilograms per hour. And then the final piece of information I had was that ethylene glycol is fed at a ratio of 1 kilogram ethylene glycol for every 4 kilograms of water entering the column. Okay, so in this scenario, let's try and identify first what are the streams that we're relating. We are relating ethylene glycol being fed, so that's stream 2, and it's for every 4 kilograms of water entering the column. And so the only place where water is entering the column is stream 1. So what I'm doing is I'm relating the mass flow rate of stream 2 with the mass flow rate of water in stream 1. So M1 water. Now the next piece of information, or the next part, is we've got that 1 kilogram ethylene glycol for every 4 kilograms of water. And so what we can do is we can consider this as a conversion factor because we're relating the ethylene glycol in stream 2 with the water in stream 1. And so just reading this out, it's going to be that ethylene glycol is fed. And so therefore we're going to say that it's the M2 dot ethylene glycol is going to equal 1 kilogram ethylene glycol for every 4 kilograms of water being fed in. So the way we'll write that mathematically is M2 dot, the mass flow rate of ethylene glycol coming in, is equal to 1 kilogram ethylene glycol per 4 kilograms of water multiplied by the mass flow rate of water. Now, if you ever are uncertain with these, let's say, conversion factors and which number should be in the numerator and which should be in the denominator, you can treat this as unit conversions, where, if you look at this, you look at these terms, you have on the right-hand side of the equation, you've got 1 kilogram ethylene glycol over 4 kilograms of water multiplied by a mass flow rate of water. And if you look, the numerator and denominator have a mass of water. And therefore, those water terms are going to cancel out, leaving me with a mass flow rate of ethylene glycol, right? Which then is equivalent to that, or are the correct units we need for M2 dot. Now, in this process specification, since I have a lot of information on the mass flow rate of stream 2, the ethylene glycol, most likely it'll be handy for me to just rearrange and move my conversion factor to the left-hand side so that I have a consolidated term with the conversion factor and the mass flow rate of ethylene glycol. And now I can obtain the mass flow rate of water later down the line when I'm trying to solve for my unknowns. So what I'm going to do is I'm just going to move that conversion factor to the left-hand side. And obviously I'm going to have to flip the numerator and denominator. And so now we've got our process specification written out mathematically. All right, great. So what we've done now is we've more or less set everything up to help us start to consider working on and solving this problem. Now moving forward, next thing we're going to do is we're going to perform a degree of freedom analysis, the final piece in order to identify whether or not we really can solve this problem. So what we're going to have to do is we're going to have to go first look at our we've got our diagram just to help us out, and we've got our process specification. So we're just presenting all the information that we have to help us with doing this degree of freedom analysis. And so now we're looking for our ISVs. So counting our independent stream variables, we see that it's going to be 7. And the way we get that 7 is that we've got 2 components in stream 1, 1 component in stream 2, and then 2 components in both stream 3 and 4. And when you sum those all up, that will give us 7 ISVs. Now when we go to our knowns, we have 3 knowns. We know the mole percent of IPA in stream 1, we know the mass flow rate of ethylene glycol in stream 2, and we know the mass fraction of IPA in stream 3. So we've got 3 knowns. And then when we look at our material balances, we're going to see that we have 3 independent material balances, 1 for each of our components. Since we have IPA, water, and ethylene glycol, that's where our 3 comes from. Now, just as a side note, technically there are 4 material balances you can write for this system. Remember, you can write 1 material balance per component, and then you always can write a total material balance as well. And then finally, we have a process specification. We've got 1 process spec, and now that we've written out everything that we know about our system, we can figure out our degrees of freedom. And so we take our ISVs and we subtract out the knowns, the material balances, and the process specifications. And when we do that, we get 0 degrees of freedom. And what that means is I have just enough information to solve this problem. So we can go ahead and work on solving the problem. Now, before we really jump into solving it, I mentioned a little earlier that there was some differences with some of the given pieces of information. And what I'm referring to are my mole fraction, my molar composition of stream 1 and the mass composition of stream 3. We have 2 different types of compositions. And if we don't change those compositions, we're never going to be able to solve this problem. And so that leads us into step 4, which is we're going to convert everything to be in the same terms. And so that may mean that you have to do all your unit conversions, or you have to make sure your mole and mass fractions are all either mole or mass fractions and not mixed together. So for us, we've got to convert that mole fraction into a mass fraction. And so starting off with stream 1, we've got mole fraction of 0.32 for IPA and a mole fraction of 0.68 for water. And in order to convert this, we're going to have to assume a basis of 100 moles. And when we do that, we're going to take the mole fraction and multiply it by our assumed basis value of 100. And that's going to give me 32 moles of IPA and 68 moles of water. The next thing we'll need to do is we're going to have our molecular weights for both of our components, which in this case are 60.1 and 18 for IPA and water respectively. And now we're going to find the masses of our individual components. So with the IPA, we've got 32 moles. We'll multiply by our molecular weight of 60.1 grams per mole. and that's going to give me 1,923.2 grams. And similarly with water, I'm going to do the same thing. I've got my 68 moles, we'll multiply by the molecular weight, and that's going to give me 1,224 grams. And now that I have those individual masses of each component, I can total those out to get my total mass of the system. And in this case, that's 3,147.2 grams. Now that I have my total mass and the mass of each component, we can solve for our mass fractions. And so for IPA, the mass fraction of IPA is going to equal the mass of IPA divided by the total mass. And so when we substitute in our values, we're going to substitute those in, and we're going to get a mass fraction of 0.611 for IPA. Similarly, we'll do the same thing for water, and when you do that, you're going to get 0.389 as your mass fraction of water in stream 1. And now, as you see in our table, we have solved for our mass fractions. We successfully converted from mole fractions to mass fractions. And now that we have that, we can move forward and start working on our problem. All right, so moving on. The next thing we're going to do to begin approaching and solving this problem is we're going to write out all our material balances. The reason why is because you've got a lot of information, you're not sure where you're going to start. And writing out all your material balances is a great place to just help you identify what things you know and and identify if there are any equations that have a lot of information that indicate you can probably start working there and you can probably solve for a value there. And just to help us out, I'm going to put our diagram back on the slide so that we can write our material balances. And so to start, we've got the IPA material balance. And in this case, we've got the mass flow rate of IPA in stream 1 is coming in, and coming out, we've got the mass flow rate of IPA in stream 3. And that's everything. The next one we have is our water material balance. And for water, we've got water coming in stream 1, and coming out, we've got water in stream 3 and in stream 4. So M1 water, the water coming in, is going to equal the mass flow rate of water in streams 3 plus stream 4. Okay, moving on, we've got ethylene glycol material balance. And in this one, we've only got ethylene glycol in stream 2, and we've got ethylene glycol coming out in stream 4. So the mass flow rate of ethylene glycol in stream 2 is going to equal the mass flow rate of ethylene glycol in stream 4. And the final material balance we have is the total material balance. And so in this case, the inlet flow rates are streams 1 and 2. So M1 dot plus M2 dot is going to equal M3 dot plus M4 dot, the two streams that are exiting my system. So we've got all our material balances written out now, and that's good. The next thing we're going to do is we're going to substitute in all my known values into those material balances. Now, when we're doing this, again, I'm going to put up our diagram of our system. And so we've got the IPA material balance, and we're going to substitute in here. So we're going to actually convert this M1 IPA equals M3 IPA. We're going to convert it into our mass fraction and the mass flow rate of the entire stream 1. And so we've got X1 IPA equals multiplied by M1 dot equals X3 IPA times M3 dot. And now I have some mass fractions of IPA. And so now I can substitute those in to my material balance. So it's 0.611 M1 dot equals 0.98 M3 dot. Now, I don't have enough information. I've got one equation and two unknowns, so I don't have enough information to solve this material balance or solve for any unknowns. So we're going to move on to another material balance. So we've got ethylene glycol. We've got M2 dot ethylene glycol equals M4 dot ethylene glycol. And again, we're going to switch it into our mass fraction and mass flow rates unless we know the entire mass flow rate of a particular stream. So in this case, we know M2 dot EG, and that's going to be 921 kilograms per hour. And we're going to say that's equal to X4 ethylene glycol times M4 dot. All right. Again, we've got two unknowns in one equation, not enough for me to move forward. So we're going to move on to our water material balance. And so with the water material balance, we're going to change it into mass fractions and the mass flow rates. And now that we've done that, we'll substitute in what we know, which are a couple of mass fractions. And as you see in this material balance, again, we have a lot of unknown terms and only one equation. So again, we don't have enough information here. And we're going to move over to our total material balance. And we'll substitute in what we know, which is M2 dot. And we are left with M1 dot plus 921 kilograms per hour equals M3 dot plus M4 dot. We've got three unknowns, one equation. Oh dear. So we've got a bunch of material balances, and yet I don't have any one equation to work with. Huh. Is there any other information that I might be able to use? Okay. So let's remove our process flow diagram just for a second, and maybe we can add in our process specification. Yeah, that might help us out, because that's another equation we can use. And if we look at it, I know M2 dot, so I can substitute in for that. And when I do that, now what I see is that I actually am able to just solve for M1 dot water, which is 3,684 kilograms per hour. And now that I have M1 dot water, I've figured out one of my unknowns, or I've begun to solve for one of my unknowns. And now that I've got my material balances all written out, I have substituted values in for all my material balances. What we're going to do is we're going to start with the equation that has the most information and solve for all our unknowns. And so we're going to take that value we had for M1 dot water, and now we're going to just change M1 dot water to be X1 water times M1 dot. We'll rearrange it to solve for M1 dot. And when I do, we're going to substitute in all our knowns, and we get M1 dot is equal to 9,472 kilograms per hour. Now that we've got our M1 dot, we have one more piece of information for our system, which is great. And what we're going to do is we're going to revisit our material balances and substitute that value in and start approaching another material balance, the one that has the most information and allows us to solve for another unknown. So let's go revisit our material balances. We go to the IPA material balance. We can have our substituted values present. And if you look carefully at the IPA material balance, what you'll see is that you have everything other than M3 dot. And so we combine a couple of terms, and now we can solve for M3 dot, and we're going to get that M3 dot is equal to 5,907 kilograms per hour. And now we've got another term taken care of, which is great. And again, we're going to just continue working with these material balances. So let's go back to our ethylene glycol material balance. Let's see what we got there. Doesn't seem like I have any new information that can help me with the ethylene glycol material balance. So I'm going to have to table that one for later. I got a water material balance. Okay, I think I have a couple of new pieces of information for that one. So let's substitute those in. Okay, and we'll combine whatever terms I know. All right, and it seems like with the water material balance, I still have too many unknown terms. So I can't use that one right now. So let's go look at another material balance that I haven't used yet, which is my total material balance. And it seems like, and let's substitute in what we know. And what do you know? We've got everything other than M4 dot. And so if we solve for M4 dot by combining all terms, we get that M4 dot is equal to 4,487 kilograms per hour. Okay. And so looking at our process flow diagram, we've got one more piece of information, which is great. And so now I'm going to just clear the left-hand side of the slides. And what we're going to do is we're going to return to one of our material balances. And I'm going to go with the ethylene glycol material balance, but you can also go with the water material balance at this point because we're honing in and we have almost all the information we need. So with the ethylene glycol balance, material balance, I can now substitute in for M4 dot, And now all I have is my X4 ethylene glycol that I don't know. And so if I rearrange everything, I'll find that X4 ethylene glycol is equal to 0.205. That's great. And now that I know my ethylene glycol mass fraction, I can do 1 minus X4 ethylene glycol to solve for my X4 water. And by doing that, we find out that X4 water is equal to 0.795. And now we have solved for all our unknowns. We have finished the entire problem. And so that's the approach I normally will take in order to solve a single unit material balance problem that doesn't have any reactions or doesn't have any additional complicated tricks. And so now you've seen my approach and you've got a new practice problem to work with, and that wraps up our problem. So thanks a lot for tuning in everybody. And I hope you have a great day, and I'll see you in the next one.